I'm Maggie Satsiris, and I'm going to be solving this problem today. So we're going to start with problem 1, when you find the speed at the bottom of the trajectory, and you start with VI at the top is equal to 0, but we want to find VI when the rope starts to catch the person. And so we know from the momentum principle that you can just solve for this velocity, and we also know that the only force acting on this system at this time is just the gravitational force. And then using our equation that the displacement is equal to V average delta T, and that V average is just VI plus VF over 2, we can approximate VF at this point. And so VF at that point will be approximately the square root of G times 80 meters, which is approximately 28 meters per second. And then knowing that our system is just the person plus the earth and the surroundings are none, since the work external is approximately 0 joules, delta E is equal to W plus Q, which is equal to 0. So you can say that delta E is equal to delta K plus delta U, and then you can set that equal to 0, and you can approximate your final velocity using 1/2 mv squared set to K. And you also know that your delta H is just 3 meters minus 9 meters. And from there, you can just solve for your final velocity to be approximately 30 meters per second. And then for problem 2, we have to find the tension force on the rope. And we know at the bottom that the only two forces acting on the person is the tension force and the gravitational force. And we also know that F net parallel is equal to 0 because the person is moving in approximately a constant velocity during the trajectory, and we know that F net is equal to F perpendicular. So since F net is equal to F perpendicular, you know that F perpendicular is equal to the magnitude of P times the magnitude of V divided by R, which is equal to the tension force minus the gravitational force. And so you can just solve for your tension force using this equation, and your tension force will be 2056 newtons in the n hat direction. And so then for problem 3, you have to solve for the tension force and the person's velocity when the rope is at 30 degrees. And so we basically do this little diagram of the person right here, and then the 30 degrees, and we just label this L2, L1, and 3 meters. We know that this is 46 meters, and so from there we divided our FG into components, FG perp and FG parallel, and then we found this height here by setting it equal to just 46 minus 46 times the cosine of 30 degrees plus 3 meters, and it's approximately 9.16 meters. And then F perpendicular is equal to just F perpendicular minus ng cosine theta, which is equal to mv squared over r, F tension. And F tension is equal to mv squared over r plus mg cosine theta, and we know that r is 46 meters, and so delta E is equal to 0, and so you can solve for the final velocity using the fact that delta K plus delta U is equal to 0, and then from there, our final velocity would be approximately 27.9 meters per second. And then you can also solve for the tension force by saying it equal to mv squared over r, and then you should get approximately 1779.9 in the n hat direction. And then for problem number 4, you have to find the stretch of the bottom, and we basically set the radius of the rope equal to 0.02 meters, and we set Young's modulus equal to 2.33 times 10 to the 8th Newton meters for a nylon rope. And then you can use your Young's modulus equation to solve for the change in L, or the stretch, which is approximately 0.323 meters in this situation. And then the stretch at 30 degrees would just be the same thing. You would use Young's modulus to solve for delta L, only you use your F tension that you got in the other problem at 30 degrees, which would give you approximately 0.280 meters for your stretch. And then for my VPython coding, I just used Lab 7, which we did for the spring mass system, and just made alterations to it by setting the ceiling, the ground, the ball, and the spring at different places appropriate to where they were in our diagram. And then I put a few more arrows to represent FNet perp and FNet parallel. And if you want to see my code, I can run it for you now. So as you can see, it just follows a simple parabolic trajectory, and yeah. So, and then all these arrows represent everything that's going on.